today is as follows. First, I will explain to you what causal inferencing means and go over the work we've done in WISE, both for ourselves and as open source for other people, to make it nicer and easier to use. And then we'll explain why it's fun and what it can do for you, and follow up with plenty of time for questions. So what is causal inference? Really, causal inference is as simple as trying to quantify the impact of an action. In the causal inference lingo coming from originally the medical sciences, the action could be, for example, sending a mailing campaign or suspending a customer because you think they're an AML risk, and something like this is referred to as a treatment. And then what we want to do typically is to see the impact of this treatment, which you may or may not choose to do, on something we describe as outcome. An outcome could be, for example, that customers spending over the next 3 months or something like that. And that's actually quite a difficult problem. And it's different to the classical machine learning problems that you're familiar with. And the reason for that is that you never observe the alternative. You cannot send and not send the same email to the same customer at the same time. So you cannot do supervised ML. And ideally, what we'd like to do is to take two universes, identical but for this action, and compare the actions that that particular customer would have taken in those two parallel universes, which differ only by whether they had gotten the email. Of course, that's not feasible. So we have to compare impact between similar groups of individuals. And the challenge is, of course, to see what does similar mean, and similar never means perfect identical. So how do we correct for that? So that's a fiddly problem. And by the way, I'm sure many of you have the same reaction as I did, which is, what is the problem? Right? You introduce the treatment as one more feature in your data set, and then you train a model for the outcome, including all the features, including treatment. And then you flip the value of that feature, and the change in the prediction of the model is the estimated impact. Well, there's a name for that in the causal inference modeling. It's called the S-learner, and it actually performs very, very poorly. And now I will go over in detail over what performs better. Overall, causal inference is a wonderful domain, which is being given a lot of limelight recently. And I do recommend you to read at least one of these books. If you're really into deep Bayesian math, then the causality book is a joy and a beauty in mathematical terms. And if you just want to get the understanding without too much math, the book of Why is the way to get there. But those go way deeper than what we'll need here. Today, we'll focus on applying this fun math to the simplest cases we can imagine. So what are the kind of questions that were even relevant here? First of all, there are two broad kinds of causal inference questions. One is when you just have a data set and you want to infer causal relationships or test for whether a causal relationship exists. And that's quite hard practically. There are ways of doing this, but even theoretically, not every single kind of causal graph can be uniquely identifiable from just observing the data. But there is work there. And for example, you can look at the causal learn library as one attempt to do that. However, what we focus on here is to assume the causal relationships. And what we want to do is to quantify the impact of the decisions. So for example, you want the causal relationship, you're using an A/B test. So the causal relationship is quite clear. We have customer characteristics, and we have our treatment. And we have full control, for example, on how we assign the treatment. It could be randomized, it could be biased according to some features of the customer, whatever. But we have full control over the treatment, and we assume that the customer behavior is affected by whether we treat them or not, whether we send them a marketing email or not. And in that case, but we want to know by how much and in what direction. And that's the kind of question we'll be dealing here. There is a second distinction to make. Do you have observability over which customers get the treatment? Because the treatment doesn't necessarily have to be something you control. To take an example, you may want to quantify an impact of the customer choosing to use a feature. And then all you can do is to make the feature available to them, but you cannot make them use it. Even so, causal methods can allow you to measure the impact of their using it, assuming you can observe whether that was the case. However, in many important cases, especially in marketing, you don't know whether, for example, a given customer saw a TV ad that you posted or a blog post. And in this case, you cannot work at customer level and you have to do time series methods. And that is another very important story. We're also doing it at WISE, the most important bit being marketing mix modeling, but we won't cover that today. What we will cover, therefore, is that causal graph is known, and we can observe which customers get the treatment and which don't. And what we want to do is to quantify the impact of the treatment at a single customer level. So there are different cases there. The most practical case, I think, or the one that's likely to be relevant to most of you, is A/B testing. Everybody does A/B testing or experimentation, and I would argue that everybody who does it now can benefit from using the tools I'm about to describe. The other option is the second case is where we have a test and we assign treatment. We have full control, but we don't do purely random assignment. For example, we already have a guess as to which particular campaign will work better, but we're not sure. And therefore, we bias the assignment of a campaign towards what we think will work for a particular customer, but we do not strictly control it. So there is randomization, but we know where it comes from. And the final case is when we can't make an experiment. For example, we are suspending certain customers because they trigger anti-money laundering check. And then when we reactivate them because because the extended examination proved it didn't seem to be money laundering, we want to know how the suspension affected their subsequent behavior. And even in that case, there is at least something we can do. The final and the hardest case is when we have self-selection. For example, we offered a discount program to people who then increase their volumes a lot. Now, the question is, did they increase their volumes because of the discount? Or did they seek out the discount because they wanted to do larger volumes in the future anyway? And it's going to be a mixture of both. And at least by controlling access to the discount, we can measure the effect. We can isolate quite well the effect of the decision and not just of the discount, which we control. So as you can see, this is getting messier, but also here we can do something useful. So now I will go into a bit into the guts of the thing, and then I will come back into what it's good for. So the guts of the thing, actually causal inference right now reminds me of when the neural networks were 5 to 10 years ago, maybe, which is there's plenty of wonderful open source libraries available, but they're not necessarily super easy to use. You really have to know what you're doing. And individual APIs for the models are, well, the polite word I would say is quirky. Plus, each of those models has its own set of hyperparameters to tune, and most of them also require regular machine learning regressors and classifiers as components to be chosen by the user, which is you. So, and providing absolutely zero guidance, only some vague guidelines as to how to do that. And so this talk is about how to overcome this and how to make this, how to tame this zoo and make it nice to use and simple. And the biggest question there is supposing you work your way through the APIs and make both models work. So you have 2 models or 10 models, each produces a set of estimates. How do you compare them? In the regular world of machine learning, you would reserve a part of the data as a test set, and then compare the model's performance over this holdout test set. And though, well, first validation, maybe for tuning, and then test in the end result. And the one which performs best on this holdout data set is the model that we think is best. However, if you cannot observe the counterfactual, so you can never directly observe the thing you're trying to estimate, which is the impact, how do you do out-of-sample testing? And that is the first question we had to solve when we embarked on this journey. There are quite a couple of things out there in the literature, each of them with its own set of limitations. And ultimately, after trying to make this work, we ended up on inventing a new one. And this new one is called energy distance. And the basic idea is super simple and generalizable. The idea is the following. Supposing you have a control set of people who didn't get any treatment. For example, people had no access to the feature and therefore couldn't choose to use it, or people who didn't get the email. And then you had a set of people who either had access or choose to use the feature or got one or multiple actual treatments. Then what you do is for that second set, you estimate the impact of the treatment and subtract it from the outcome. And your expectation then is the joint distribution of features and outcomes after this correction should be identical over the 2 sets. That's a lot of math. But fortunately, then there is a method that's already been implemented for testing the identicalness of those distributions. And empirically, we found that this method not only generalizes to all the different problems we discussed, which the other ones don't, but also leads to best estimates. So if we use this to select the best model, then the actual scatter plot of actual versus estimated effects on synthetic data looks the best. So far, so good. Now we can compare models. Once we can compare models, we can select the best one. And to do this, we need to provide a unified interface for all the models we're comparing, so we can iterate over them, and then we do search. And the rule number 1 of data science is to never reinvent the wheel. So we took our actual models, mostly from the wonderful EconML library by Microsoft. And so there we have all of the models for the all of the conditional treatment effect models and a couple of instrumental variable models. And then additionally, we also implemented the transformed outcome model ourselves, because I think that's a very, very important model. And then we use DoWhy as a consistent high-level interface to the EconML estimators, and FLAML as both a way to search across models and model hyperparameters, and as a way to fit the regression models that the components need. So therefore, getting all of them to work together, of course, was quite fun. But this way, all we had to do is to put them together, and put them together with the score I described in the previous slide. And the end result is the library called auto-causality, though that may be overclaiming, because we're not automatically inferring causality, just automatically fitting the models. So we might rename it. But it's there, and it's being used in WISE, and it's being improved as well. And it's fully open source, so you're welcome to try and use it. One thing I would ask is, if you do try it, you actually wait till next Monday, because we're merging another feature tomorrow, so documentation might change a little bit. So, why should you care is the most important question in a talk like this. And this is what the second half of this talk will be devoted to. Now, each organization tries to improve the product, and there is no way where it will work. So you have to do testing. What is the classical way of doing testing, which has been described as the golden standard for learning cause and effect? You first randomly split your audience into test and control groups. Or maybe if you have multiple options for the new thing, you have one control group and multiple test groups. You subject the test group to a treatment, such as a different UI shape, marketing email, and so on. And then you measure the average distance in some kind of a target variable that you care about, such as click-through rates or spending in some period afterwards, and so on, in between the control group and the different test groups. And because the difference is often quite subtle, you have to choose sample sizes which are large enough for the difference to be statistically significant. And so it might have to wait for a while until you get to the sample size. So far, so good. That comes with issues. One problem is that you treat all the differences between customers as noise. For example, if whatever you're doing, some customers love it, others hate it, you may just see zero average impact, no significance. And you could also say it's wasteful, because typically you might need to collect and process hundreds of thousands of data points just to learn a Boolean. Is it significant? Or maybe a single number, which is the average impact of a change. Also, it can be a hard sell to product teams, because to do the A/B testing in the first place, we need to build the new thing first. And once we've built it, presumably we have a conviction that it'll be useful. So what's the value? What's the value add of the test? Now, how can the modern causal inference estimators help with all that? First of all, the key feature of the causal inference models, for example, from EconML, as used in auto-causality, is they don't just do average impacts, they estimate impacts per customer, or rather per customer feature vector. And often they also supply confidence intervals, and even if they don't, you can get those by bootstrapping. This means that all you need to do is to take this very same precious data set you collected during the A/B test. Then you enrich it with customer feature vectors, throw causal inference at it. And what you get is customer segmentation by impact. So now the customer heterogeneity becomes data that you learn from, and not just noise to be averaged over. Here you see an example. So this is from real data for volumes after a certain marketing email in the different time intervals, 30 days, 60 days, and 90 days. And this is out of sample. So we have trained, so the auto-causality has selected a particular model that works best on the training set. And then what we do is we use this model to generate recommendations for an out-of-sample subset. And that's an out-of-sample subset where we already had randomized, so we know what the outcome is. Then, so for each, so now out-of-sample, it tells us which customers should we send this email to, and which ones shouldn't we. And then in those two subsets, we can do a naive estimate of the outcome. And what we are seeing, so as naive estimate in each case is just the average difference between treated and untreated customers. So the intuitive thing. And what we are seeing indeed that for the customers for which the model says it's a good thing to treat them like this, we see positive outcomes. And for customers for which the model out of sample said, no, this will not be useful, we see negative outcomes. And the most fun thing is the average outcome is very nearly zero and very nearly insignificant. So by segmenting your customers by impact, you learn something. The other good thing that can come out of this is that by treating customer variability as data, you get sharper estimates for your impact, even for the average impacts. Let's suppose you don't care about segmentation, you just want to know the average impact. But even for average impact, because you're now using your customer features as data, you get sharper estimates. And sharper estimates mean smaller sample size is significant. And therefore, less long runtimes for tests for significance. Now, we're still working on quantifying that. So the below graph shows that on synthetic data, we know exactly the actual error. So the actual impact and therefore the error. The estimate by using a fancy method is much tighter, much less noisy than the naive method of just treated minus untreated. Of course, in real data, you don't know what the true estimate is. You can approximate it by bootstrapping. The bootstrapping estimates of standard error are known to be on the low side, but still, this can help you get there. So that's another benefit, shorter runtimes of tests. Finally, A/B tests is not all there is to it. Because the problem with an A/B test, it must stop one day. If you want to start learning from what, if you want to start using what you learn, you can just stop the test and start using A or B. What you can do here is that you don't have to stop a test, and you don't have to wait for the test to finish. Instead, what you can do is to, as soon as you get a sample from a test, start random, is the model will give you a confidence that a particular customer, which is the best thing to do. And you don't have to be certain. Maybe it's even a 10% higher probability that treatment will get better results than doing nothing for the customer. And if so, you get a 10% higher chance of setting up the treatment. So you just scale the treatment in according to a certainty of what is the best thing to do. You scale treatment probabilities. And then as you get more certain, your assignment gets more deterministic. And the lovely thing is that by using this causal inference math, you can still learn from these increasingly biased data sets as well. The final and the most trickiest case is hidden confounders. So impact of customer choices. And that's the thing I've mentioned before, which we offer a new product feature, and then which makes a certain thing easier to do. And then we see that people who choose to use that feature do larger volumes. And then they used to do before, and then other customers with similar features. Now, is this because, is it caused by the feature? Or to what extent is it caused by the feature? And to what extent are the customers who want to do large volumes anyway, all of a sudden, are self-selecting to use that feature? Now, that's a hard question. And if that's all we know, it's probably impossible to answer. But let's suppose we want to make the feature available to half the customers. Then we have an additional data point, and we can use that to measure their impact. And now there are two ways. The first one is the lazy way, which is we're saying we don't even bothering of measuring the impact of the choice. We measure the impact of making the feature available. And that is just like another A/B test. We control precisely who can use the feature, and that's it. And then we can measure the average impact of making the feature available, divided by the fraction of users who chose to use it, and there is your impact of customers choosing to use it. Done. However, let's suppose you want to go one smarter and want to have not just the average impact of customers using the feature, but the dependence of that impact on customer features. And that's what's called instrumental variable approaches. And again, there are models for this. And these models are included in the auto-causality library. Now, of course, all of this would be very hard to justify showing to you and open sourcing and putting the work in if it wasn't valuable to WISE itself. And we've been working on this for just about a year now. And right now we have several projects running. So what we're doing is we are improving CRM campaign targeting, analyzing their impacts. And we are improving the targeting of referral reward programs, which I'm going to go into a bit more detail shortly. And we have also looked at impact of customer suspensions on retention and future volumes. And all of this, and now we're also looking on the product side into improved analysis of A/B test results. So referral rewards is a use case we shall discuss in a bit more detail, because it's fiddlier than you might think. So first of all, there are more players there, because we offer the reward for referring customers, but we offer the referral to the person who does the referring. So then the person who does the referring must make the choice of doing the referral. Then the person who was referred must make the choice of actually doing business with us. And then we need to trade off the cost of the referral reward against the potential benefit of these new customers. So it's quite tricky. Now, what do you even model here? And so we tried, and so as usual, if you don't know what to do, try a bit of everything. So we tried several things to model several causal things. And if you don't know the ground truth, what do you plot? How do you compare your models? Like energy distance is one, but here we're looking at a different metric because it's a bit of an older plot. But basically, both x and y axis is a quality of fit for the model, or a metric for the model, which makes sense for causal data sets, and larger means better. And then the black asterisk is the dummy model, which is just purely random. So the average impact is estimated from the data set naively, and then the individual variations are random. So at the very least, the model would have to do better than random for us to trust it. And you see that the performance is quite different for different metrics. For just referrals, so did this customer, how did us offering a larger reward increase the probability of a customer referring somebody? Actually, most models are doing much worse than random. And only one model does better than random, but frankly, I think this might be a fluke. So so I'm not going to go with that. The next one, which is, what is the chance, what is the impact of a larger reward on the probability of not only the customer, not only existing host recommending somebody, but that somebody actually doing a transaction with us, which arguably is the more relevant metric. Here you see some models do better than random, some do worse, and usefully, the validation and the test performance are very strongly correlated, which means that there is a hope that this is a useful run. And finally, we'll look at the kind of metric that we might be interested in as well. It would be very useful if we knew this, which is, what is the referral, what is the total volume, what is the impact of increasing a reward on the total volume by people referred. Here, however, you see that the metrics are all over the place. So the test and the validation performance is virtually unrelated by the different models, which leads us, and that's just because the volumes are too volatile compared. There's so much volatility in the volumes that this volatility obscures the causal relationship we're trying to track here. So what we're going to do, so what we're going to do there is then do a two-stage model. We first, that's what we're working right now, is we first fit the likelihood of, so we first fit the causal model of increasing the reward on the customer to whom the reward was increased, referring somebody who will convert. And then we are fitting a regular ML conditional model for just those who did convert. So let's suppose this customer was referred by a host with this feature vector. What is the likely lifetime value or volume or and so on of this customer? And here, because there is no causality involved, this is purely an old school supervised regression. So you can do much simpler problem, depending on how many customers we have in the converted sample. We can even use regression or some of the fancy methods like gradient boosting. Here again, we see that out of sample, the model performs quite well. So the impact, so the average impact for the of the referral on people where the model says there's no point is insignificant, and for those where the model says yes, there will be an impact, the impact was nice, positive, and significant. On the other hand, and this is quite interesting, if we just try to build a simple decision tree after the fact, can we just pick a couple of features to explain the impact? This actually does terribly. So this is not very useful at all. So there is no one single one or two features which allow us to explain the impact nicely. And this also means that the old school method of just doing an A/B test and then doing a pivot table by all the different features and by hand trying to click around on it and see which features seem to matter most will not allow you in general to see very well what matters. So yeah, that's just okay. So here I just say this is the kind of two-stage approach. And by the way, that's quite generally a useful trick. If the thing you're trying to predict, like volumes, or is in itself quite volatile, you might want to split the causal analysis in two stages, where the first one is you try to predict the causal impact on something that is less volatile, like conversions. And then you do a conditional model for those who converted. You just do a regular regression model for just those who converted. And then by stringing the two together, you get the full picture. So the lessons learned is, first of all, you need quite large instances to run the fits. So like as with all AutoML, you need, all AutoML is RAM hogs and CPU hogs. And here even more so because you're actually doing nested AutoML. You're searching over the causal models, and each causal model is doing a search over component models. One tricky thing is that you need to be quite sure that if you're fitting it and saying my treatment is randomized, you have to be sure it's randomized. But for example, if you're having randomized treatment from two different regions, and you are in each region you randomize treatment assignment, but the fraction of those treated will be different across regions, and then you pool this data set, then treatment assignment will no longer be random across the pooled data set. And if you then fit a model which assumes the treatment is randomized, you'll get absolutely wonderful in-sample fits, but which will perform absolutely horribly out of sample. So if that's what you're seeing, you see wonderful in-sample performance and shit out of sample performance here, probably at causality leakage somewhere. Right. So to summarize, just a couple of the highlights of why I think this is useful and this is fun. You can use this for A/B testing specifically. You can use exactly the same data from the tests you're already running or have run, just enrich it with customer features. And then by using this kind of causal inference AutoML, without figuring out all the quirks of every single model, you can estimate causal impact as a function of customer features, allowing you to segment your customers by impact. You can also learn fine-grained impact like this from biased random sampling. So you don't no longer have to stop your tests. You can always keep running tests and keep learning from them, while at the same time using what you've already learned. But also, if you don't care about segmentation, you get less noisy impact estimates, and therefore you can your tests will need to run for less long, and that's money in the pocket.